Hi everybody. Thank you so much for joining us for today's webinar. My name is Chelsea Pedersen, if we haven't been able to meet before. Before we get started with today's presentation, which I'm sure will be wonderful, we'd like to thank our sponsorship from the IAS, which allows us to offer all of the resources free of charge. So very accessible to anybody who's interested in being part of this community. Please forward them that information. And take a look at the website. It has tons of stuff for online lectures. There's different virtual field trips, lots of good stuff. So make sure and check it out. And today's lecture is by Dr. Zhuzhu Wu, who's a postdoc at the Energy and Environmental Institute at the University of Hull. He received his MSc from the Eastern China Normal University and then moved to the University of Hull for his PhD, which he received in 2018. His research focuses on the intersection of abiotic and biotic processes with a special focus on morphodynamics. Today, he's going to talk to us about really cool flume experiments and the effect of discontinuity on mixed clay and sand substrates. And with that, Zhuzhu, I will give you the mic and wish you best of luck.
Yes, thanks very much for Chelsea's introduction. And hello, everyone. Today is my great honor to be here amongst you, and it's indeed my privilege to represent our team to share the latest experimental results in the SED online webinar, which is actually a big stage. And sorry, just open the pen. So ripples are the primary and sedimentary features, which are often characteristic of the forming flow parameters. They are very common in the nature because they could be generated under the current, waves, and the flow combined with waves and currents. And this photo was taken at the Humber Estuary in the UK. As you can see, during the low tide water, this big sandbars was covered by the ripples. We are interested in ripples because they have great applications. So these are the two 3D scanning platforms from the sandbar, as in the photo I shown in the last slide. So compared to the flat bed, the formation of ripples can increase the bed roughness, which will affect the real bed velocity, as well as the sediment transport, including the suspended sediment transport and the bed load transport. So proper prediction of the ripple size and therefore ripple's roughness will be very important for a good performance of the sediment transport in the estuarine or in the coastal environment. Apart from that, ripples could be preserved in the rocks, as shown in these beautiful photos taken by Andre. And researchers can use the inverse relationship between the ripples and the hydrodynamic conditions to reconstruct the pioneer environment based on the ripple marks. Actually, indeed, quite a lot of researchers and previous researchers have provided excellent information about the ripples dynamics, but most of them only focused on the clean sand ripples, which is quite far away from the reality. As shown in this map, you can see the cohesive sediments, such as the sediment mixed with sand and mud, they are widespread across the world. So how does the cohesive clay affect the ripples dynamics? And recently, some researchers have put their attentions on the bed foam dynamics with the cohesive clay, and there are 4 examples. The first 3 investigated how the cohesive clay affected the bed foam development under the current. And the last one, the researchers focused on the wave ripples development on the mixed clay and sand substrate. However, to date, very few studies focused on the repose dynamics with cohesive clay under the combined flow, even though the combined flow is very common during the storms. So in order to fill these knowledge gaps, we conducted a large-scale flume experiment at the Total Environment Simulator at the University of Hull. And we want to quantify the repose development rates for the different initial clay content. And the second objective is to determine the relationship between the equilibrium repose size and the initial clay content. And lastly, we want to relate the repose development to the changing bed compositions. So this is the sorry, I just changed to the laser pen. So this is the top figure shows the plan view of the experiment setup. So the tank was divided into 3 equal-sized channels with 1.4 weight. And during the experiment, both wave and current moving the same direction from right to the left. At the end of downstream, there was an artificial beach, which can reduce the wave reflections. And in the middle area, there was a 6 meters long section mixed with sand and clay, and in which there was a 2 meters long of the test area. And most and in the upstream, there was a 1 meter long of the section filling with the gravel, and the downstream there was a section of clean sand section with 3.7 meters long. And most of the instruments used in the experiment were mounted on this gantry in the test area, and we got the ultrasonic range system, which contains 32 probes as shown in these black squares. And this photo shows the URS and probes in the center channel. And during the experiment, at the preset time, we just stopped the wave and the current and moving this gantry. So the URS probes can scan the 2 meters long section area and to acquire the repose development information. Apart from that, we also have 3 vector channel profilers in each one for each channel, as shown in these photos. So the vector channel profilers with 4 sensors can record the 3-dimensional flow velocities during the experiment. And apart from that, we also have 8 acoustics water level sensors, as shown in these open circles. They can record the water surface elevations during the experiment. And the bottom figure shows the side view of the channel 1 and the initial bed level thickness of 0.1 meters, and the water depth was 0.4 meters. After a control experiment, we started to move the clay back into each channels and mixing the clay and sand using this hand mixer for concrete properly, and followed by using a channel wide wood to roughly flat the bed, and then I just used the trowel to properly flatten the bed. And this is my colleague Roberto, and he took a more heavy work by preparing the sediment bed with higher clay content. So after a labor-intensive day, we have prepared 3 sediment beds with different clay content. Apart from that, we also collected the sediment cores using syringes from the sand mix and section mixed with the clay and sand, and as well as the clean sand section. So during the experiment, when we stopped the waves and the current, we also collected the sediment cores. And at the end of the experiment, after draining the water, we collected the sediment cores as well. And this is a photo to show the syringe size of the sediment cores with the maximum length about 10 centimeters. And these are the 3 sediment cores collected in the channel 2 of round 2 with the initial clay content about 10.6%. So for the sediment cores collected from flatbed and the ripple trough, we slice down into 1 centimeter intervals for the further grain size analysis. And for the portion corresponding to the ripple's crest, we slice down into 0.5 centimeters to provide the better resolution within the ripples. And this table shows the experimental parameters. We used the consistent hydrodynamic conditions from round 1 to round 3 with the wave period of 2 seconds and the wave height about 0.17 meters. And we also used the orbital velocity at 5 centimeters above the flatbed at the beginning of the experiment, about 0.32 meters per second. And the depth average current velocity was 0.2 meters per second. And for round 1, this was a control experiment in which we used the pure sand with the D50 about 450 micrometers. And in the channel, in the round 2, we plan to prepare 3 very high initial clay content beds. However, I didn't mix very well in this channel 1, so we have to abandon this channel. So the initial clay content in channel 2 and 3 of round 2 were 10.6% and 12.3% respectively. And during the round 2, during the experiment, quite a lot of clay moving out from the bed and suspending them into the water. So after we draining the water, we remix the sand and the remaining clay in these 3 channels and generated the 3 brand new beds, but with lower clay content compared to their counterparts in the round 2. So the initial clay content in round 3 was 5.7% for the channel 1 and 8.5 for the channel 2 and 11.6 in the channel 3. Okay, let's move to the experimental results. Firstly, we focused on the ripples development with the initial clay content lower than 10.6%. The top figure shows the ripples height development, and the bottom one shows the ripples wavelength development. And the red line shows the clean sand ripples development in the control experiment. So as you can see, the clean sand ripples appeared from the flatbed very quickly, and the ripples height increased and developed very quickly as well. And both ripple height and the wavelengths reached to stable before 200 minutes. And for the lowest clay content of 5.7%, as shown in these yellow lines, you can see both the ripples height and the wavelength development curves were quite similar as the clean sand ripples. And then moreover, the final ripples height and the wavelengths were close to the clean sand ripples as well, with the initial clay content increased to 8.5%, as shown in these blue lines. The first appearance of the ripples apart from the flatbed delayed around 1 hour, and moreover, the ripples height and ripples wavelength development was decreased compared to the clean sand ripples, which contributed to ripples height and wavelengths reached to stable after 400 minutes. However, for the final ripples and wavelength height and wavelengths, their dimensions are still quite close to the clean sand ripples as well. For the clay content, about 10.6%, as shown in this green lines. You can see from and the repose height and development rate further decreased from 90 minutes to the 200 until the 230 minutes. As shown in this green line, you can see the repose height was stuck just below 4 millimeters, followed by a rapid increase in the repose height, and over 800 minutes, repose height reached stable, and the final repose height was very close to the clean sand repose as well. However, for the repose wavelengths, which was lower than the clean sand repose wavelengths. And this plot shows the planform geometry of the clean sand repose in the control experiment. As you can see, these clean sand repose were typical two-dimensional repose with quite straight and continuous and creased lines. And at the initial clay content of 5.7% bed, the final repose was still two-dimensional. And for the two higher clay content bed, this repose was still two-dimensional, which with the planform geometry quite close to the clean sand repose. Apart from the planform geometry, we also quantify the cross-section geometry as well. And we introduce the repose symmetry index, which equals to the repose stoss side length against the repose lee side. The RSI value equals 1, which means the repose is imperfectly symmetrical. And apart from that, we also introduce the repose steepness, which equals to the repose height and over the repose wavelengths. So as shown in this table, you can see the repose symmetry index for all of the repose are over almost 1.4, which means this repose were slightly asymmetrical, and the RSI value was independent with the initial clay content. And for the repose steepness, the RS value was independent with the initial clay content as well, with the RS value standing at around 0.12. So for the repose development with the initial clay content over 11%, in order to compare, I just keep the clean sand repose development curves, as well as the repose developed from the 10.6% initial clay content. So for the initial clay content over at the 11.6%, as you can see, the first appearance of the repose from the flatbed further delayed around 1.5 hours. And then, since then, the repose height was stuck just below 3 millimeters. And this trend was quite similar as the one from the 10.6%. As you can see, they were stuck at 4 millimeters. However, unlike this repose, the repose height was stuck in around 4 millimeters until the end of the experiment, just weakly increased to just above 5 millimeters at the end of the experiment. And for the wavelengths, the final wavelengths from the initial clay content of 11.6% can develop close to the ones from the initial clay content at 10.6%. However, it's quite shorter than the clean sand wavelengths. At the highest clay content at 12.3%, the time of delaying repose appearance from repose and further delayed around 2 hours. And moreover, the repose wave height was stuck at just around 3 millimeters until the end of the experiment. And for the repose wavelengths, the wavelengths of the repose from the highest clay content was the lowest, compared to which is quite shorter than that of the clean sand repose wavelengths. And as I mentioned before, the clean sand ripples, which were two-dimensional in terms of the planform geometry, and but for the planform geometry for the ripples at the highest clay content bed, this planform geometry heavily changed. They looks like the barking shaped ripples with discontinuous crystalline and because the elevation in this platform is quite narrow compared to the clean sand ripples for the elevation scale bar. And for the initial clay content at 11.6%, these ripples were quasi two-dimensional with straight but discontinuous crystalline. And in terms of the cross-section geometry, as we can see, for the ripples symmetry index, the ripples from the highest clay content, they have the ripples symmetry index were slightly increased, which means these ripples were more asymmetrical. And most importantly, the ripples steepness for the ripples developed for the two highest clay content significantly decreased to just 0.05, which means these ripples were quite flatter compared to the clean sand ripples. And this plot shows the relationship between the equilibrium state and the initial clay content. The top left shows the equilibrium wave height with the function of the initial clay content. As you can see, with the initial clay content below 10.6%, the ripple's height was independent with the initial clay content. And there is a discontinuity in the ripple's height with the initial clay content over 11%. As you can see, the equilibrium ripple's height collapsed at the highest clay content at 12.3%. Which the value was 3.4 millimeters, which was 4 times shorter than the clean sand ripple's height. And in terms of the ripple's equilibrium wavelength lambda, as you can see, with the initial clay content lower than 8.5%, the initial clay, the ripple's wavelength was between 120 and 130 millimeters. And with the initial clay content increased, the equilibrium wavelength linearly decreased. And the bottom two plots shows the ripple's development rate against the initial clay content. The ripple's development rate, which equals to the ripple's equilibrium dimension over the ripple's equilibrium time. So both the ripple's height development rate and the ripple's wavelength development rate decreased with the initial clay content increased. Okay, let's move to the change in the bed clay content. Firstly, we focused on the initial clay content of 5.7%. This plot shows the vertical profile of the clay content below the flat bed just before the experiment. And the gray dot denotes the mean clay content at each depth, and the horizontal bar denotes the one standard deviation from the mean. And the gray vertical line represents the mean clay content through the whole bed. And the vertical dash gray line denotes the one standard deviation from the mean. So the sediment course demonstrate quite consistent clay content from the top bed to the bottom bed before the experiment start. At 5 minutes, most of the bed still keep the flat, and the black dot shows the clay content below the dynamics flat bed. And the sediment course shows the top 15 millimeters, the layer with the clay content was just half of the initial clay content. And below this layer, the clay content increased with the depth. And some small ripples were generated at 5 minutes as well. And the blue dot shows the clay content below the ripple's crest, and the red dot shows the clay content below the ripple trough. The sediment course shows at the top layer, just below the ripple crest, in this layer with the 100% clay lost. However, the ripple's base still kept some clay content. And the yellow horizontal lines denote the ripple's base. So the layer just below the ripple base, the sediment course shows it's already lost about 40% of the clay content compared to the initial clay content. And below this layer, the clay content were quite close to the initial clay content. So at the 50 minutes, with the ripple's height increased, the sediment course demonstrate all of the clay was already lost in the ripples. And the layer below the ripple base, it continued to lose the clay. And from 290 until the end of the experiment, the sediment course displays the clean sand ripples over the bed mixed with clay and sand. And moreover, the sediment course also demonstrate a downward expansion of the layer below the ripples, losing the clay content even at the end of the experiment. So for the initial clay content increased to 10.6%. At 50 minutes, the bed still remained flat. But the sediment course demonstrated the top layer has already lost some clay content. At 290 minutes, very small ripples formed, as shown in this. The profile of the clay, content are quite similar as the one at 5 minutes from the initial clay content of 5.7%. As you can see, the ripple's crest was clean sand, but the ripple's base still kept some clay content. And below the ripple base, the layer lost some clay content. And from the 650 minutes until the end of the experiment, the sediment course demonstrated a transformation of the clean sand ripples. And moreover, compared to 5.7%, the sediment course demonstrated a slower downward expansion of the layer losing clay content. At the highest clay content of 12.3%, the ripples actually were generated at 219 minutes and 650 minutes. However, they were too small at that time, so it's impossible to sampling sediment cores from the ripple's crest and the ripple's trough. But the sediment cores demonstrate a decreased trend in the clay content at the top layer of the bed. At 1190 minutes, we drained the water and we can collect the sediment cores from these tiny ripples. And the sediment cores shows the ripple's body kept around 8% of the clay content. And the layer below the ripple's base lost a amount of the clay content, but still had quite a lot of clay in this layer. And at the end of this experiment, the clay content in the ripples decreased to just 1%. However, the layer below the ripple base still keeps a very high clay content, which means that this layer still has higher beta cohesion to resist the flow erosion, which contributed to the limitation of the sand supply to develop ripples. So at the end of the experiment, there was still tiny ripples. So the sediment course demonstrate the clay loss even from the layer very far away, far below from the ripple base. And this deep cleaning of the bed clay, we suppose is due to the clay winnowing. And the clay winnowing can resuspend the clay from the bed and into the flow, and just leaving the sand particles below the rippled bed. And but it's apart from the ripples moving out, actually apart from the clay moving out, sorry, clay can also re-enter into the rippled bed as well, as shown in these two plots. These two plots shows the vertical profile of the sediment cores collected in the sandy ripples at the pure sand section in the round 2, at the end of round 2 and round 3. And the sediment cores demonstrate a small amount of the clay can stored in at the layer just below the ripples. So we suppose this clay re-entered into the rippled bed with the hyperreic flow, as shown in this hyperreic path based on the previous study. So we suppose some clay carried by this hyperreic flow and stored in this layer. So there was a dynamic balance between the clay loss and the clay gain. And in the present conditions, the winnowing induced the clay loss was dominated and forming the clay loss layer with the very big thickness. Actually, such clay dynamics also existed in the below the wave rippled bed, and this picture shows the sedimentary texture below the equilibrium wave ripples modified from the Wu et al. 2018 research. As you can see, below the wave ripples, there was a clay loss layers. However, below this layer, there was a clay enriched layer, which means quite a lot of clay can moved downwards and stored in this layer. However, such clay enriched layer was absent below the combined flow ripples, which indicate under the combined flow, the clay winnowing may be very high in very high efficiency compared to the clay winnowing, which may be lower under the waves. So, our experiment demonstrated two distinct equilibrium ripple size, which depend on the initial clay content. And in the present hydrodynamic conditions, the threshold clay content was around 11%. And actually, these threshold values could change with different hydrodynamic conditions. And regardless of the exact threshold clay content, we developed two conceptual models for the combined flow ripples development. If the initial clay content lower than the threshold clay content, the small ripples formed in the incipient stage, which are characteristic of the very clean sand crest. However, the ripple base kept some clay content, and the layer below the ripples in this stage with a thin layer and start to lose some clay. And in the growing stage, the ripples has become to sandy ripples, and the layer losing the clay content gradually expanded downwards. And in the equilibrium stage, ripples have already changed and transformed to the clean sand ripples. And due to very higher clay winnowing, the bed, even the deep clean of the bed clay contributed to form very thick clay loss layer. And if the initial clay content higher than the threshold, which means the bed have very high bed cohesion, which can resist the flow erosion. So the bed can remain the flat for a long period. Once the ripples formed in the incipient stage, these ripples still kept quite low clay content. And due to the higher clay content below the ripples, the limitation of the sand supply contributed to these small ripples can keep for a long time, even in the equilibrium stage. But in this stage, ripples has already most of the clay content. Actually, the discontinuity observed in our experiment maybe also could be happened for the current ripples. These two photos were from the experiment from Bass et al. 2013. The left one shows the equilibrium clean sand ripples. They were three-dimensional and they were lingered with the ripples stiffness about 0.13. And the right one shows the planform geometry from the initial clay content about 16.2%. As you can see, these ripples are quite different from the clean sand ripples. And most importantly, the ripples stiffness was only 0.05, which means these ripples were quite flatter compared to the clean sand ripples. This is quite similar as we found for the combined flow ripples with the clay content over 11%. And these two-dimensional ripples also quite similar as the clean sand ripples in their incipient stage due to the limitation of the sand supplying from the bed below the ripples. These small ripples only can keep very tiny until the end of the experiment. So, in our experiment, we found with the initial clay content lower than 10.6%, the ripples dimension and the geometries are very close to the clean samples, which means the existing ripple size predictors are still available for these ripples. However, with the initial clay content over the 11%, we found the discontinuity in the ripple's height, and the ripple's height heavily decreased, which means the existing ripple size predicted possibly overestimate the ripple height. So, the predictors of the ripples need to improve by incorporating of the influence of the clay. And again, with the initial clay content lower than 10.6%, the ripples stiffness was similar as the clean sand ripples. So the existing sediment transport models is available for these ripples as well. However, due to the significantly decrease in the ripples stiffness, so the existing sediment transport models needed to further improvement for these small ripples. And in the field, if we found some clean sand ripples, combined flow ripples, if we want to reconstruct the pioneer environment using these ripples, we must be careful because if we found the clean sand ripples, we need to check the layer just below the ripples. If we can find there is a clay content in the layer. If yes, we must bear in mind that these ripples could possibly were generated in the muddy environment instead of the clean sand environment, even though you found the clean sand ripples. And for the initial clay content over 11%, if you found the very tiny ripples in the field, you needed to check the clay content in the ripples. if you found and the clay content in the ripples, you should be very careful and think these ripples may not be generated under the weak condition. So if we reconstruct the pioneer environment based on the ripples from the cohesive environment, we must be more careful. And for the next, so this is the clean sand ripples phase diagram and from the Parallel et al. 2014 research to show the different clay and clean sand bed forms. And for the next generations ripples phase diagram, we want to introduce the third axis to show how the clay, initial clay, affect the ripples and bed ripples phase diagram. And I mentioned before, we found that if under the present hydrodynamic conditions, with the clay content lower than 11%, and the present phase diagram may be still available for the ripples from the clay content and bed. However, if the clay content higher than that threshold, so we need to improve the present phase diagram. And most importantly, if we change the combined flow induced bed shear stress, for example, if we increase the bed shear combined flow bed shear stress, the threshold of the clay content can change. They could be increased. But as well, if we decrease the combined flow shear stress, this threshold clay content may be decreased. But so far, we have no idea about the exact threshold values and the exact relationship between the threshold value and the different boundary layer conditions. So in our next research, we will focus on the threshold clay content. To summary, we found in our experiment discontinuity in the equilibrium ripple height with the initial clay content over the 11%, with the significantly decrease in the ripple's equilibrium height and the ripple steepness. And secondly, we found in Germany, there was a decreased trend between the clay content and the ripple's growth rate. And if the clay content lower than 10.6%, we found that the equilibrium dimensions and the geometry of ripples were quite similar as the clean sand ripples. And our sediment course demonstrate the transformation of these large equilibrium ripples with 100% of the clay loss. And strong winnowing induced the clay loss, result in the deep cleaning of clay at the layer even far below from the ripple base. And if the initial clay content over 11%, we found very small and flat equilibrium ripples were development in the experiment, which were quite different from the clean sand ripples. Okay, I wrap it here. Thanks for your attention.
Thank you, Juju, for such a great presentation. It sounds like we're going to be looking forward to some new experiments coming up soon. So you can reach back out to us and give us sort of an update if you'd like.
Thank you.
So I definitely have some questions, but it looks like people are already interested in the chat. So let me go to theirs first. And we have our first question from Ross Campbell, coming from Queen's University in Canada. It says, thanks, Juju, for a very fascinating talk. You said you suspect that the critical clay content for the observed nonlinear change is specific to the wave and current conditions. What are your guesses about how it might change with different hydrodynamics?
Yes, I think this is a very interesting, very good and interesting questions. And actually, as I mentioned in our experiment, in the slides, we don't quite yet know how the the threshold, the clay content change with the hydrodynamic hydrodynamic condition. But as in my last the slides, I also show they may be increased with the hydrodynamic forcing and decreased with the hydrodynamic forcing. But in the nature, this situation may be more complicated, as in the nature there was the biological cohesion, which affected this threshold value as well. So I think, as I mentioned, we need more laboratory work to find any relationship or even linear relationship or non-linear relationship between the threshold content and the hydrodynamic conditions. Hope this I answer your question. This is what I guess, to be honest. This, as I said in my next research.
Yeah, hopefully you can give some further insight to that question with the next steps in your study. Okay, next question comes from Val in Oslo, Norway. He says, your ripples and work are fascinating. I might have missed it, but can you explain why the change in height of the ripples and the change in wavelength are so different when increasing the clay content?
Oh, yes, I think this is very closely to the layer just below the ripples, because this layer is very important to supply the sediment to develop the ripple height. As you can see, below, as the initial clay content below the 10.6%, and the winnowing efficiency may be slightly decreased with the increased clay content. So the ripple's height just slowly decreased with the clay winnowing out. But for the initial clay content, over 11%. So the very high, very strong bed cohesion in the bed and prevent this is what I guess, and the clay winnowing. And so this what we demonstrate in the sediment course. The layer below the ripples still has very high clay content, which means the high bed cohesion, which prevent the ripple and sediment supply to the ripples. So that's the main reason for the prevent the ripples development the height. And in terms of the ripples and wavelengths, in generally speaking, though, there is a slightly decrease in the ripples wavelengths, which I think is close to the ripples height as well, because for the small ripples, their wavelengths was quite slower than the fully equilibrium large ripples.
Okay, so with a more cohesive underlying bed, you're going to reduce the ability to increase the ripple height.
Yeah.
Okay. Good. So now that we have a quick break in our questions on the chat, and you guys can keep typing those in as much as you'd like, I'm going to ask just a couple of my own. So especially in those plots, I don't know what slide it was, maybe something around 12 or so.
Yeah, I can come back to. I can come back.
You showed the different amount of initial clay content and how that resulted in differences in your ripple height and the wavelength.
This one you mean, Chelsea?
No, a little bit earlier, I think.
The result, isn't it?
Yes, here. Okay, so I was curious how you felt about your experimental duration, and if you think that all of the systems really reach sort of like a steady state or an equilibrium.
So you mean how I decided the equilibrium state?
Yeah, because if you look at the let's see, the 2000 minutes.
Yeah.
Especially those green lines with the clay content of 10.6. It seems like you're actually still changing a bit. So is it really?
No, this is a very good question, to be honest. I think I just prepare a slide especially for you this question.
Oh, you're ready for
me. Yeah, exactly. Actually, we decided the ripples equilibrium not by eye. actually by the mathematical method, as you can see, we use these equations developed from Bass et al. 2013 research. So we use this asymptotic curve to fit the sky and the scatter plot scatters, and then this curve can decide when the ripples reach equilibrium, and we can get this fitting coefficient from the equations. For example, for this one, for the ripple height, we can get the equilibrium ripple height about 40 millimeters, and the equilibrium time over 800 minutes with very high confidence with about 0.95. Yeah, even the same as for the ripples wavelengths development as well. So we use
was your cutoff, your R squared cutoff value then 0.8, or did you have a cutoff value?
Sorry?
I was just wondering if you had a cutoff value then for your R squared value, because for your wavelength, the bottom plot of 0.81, I mean, it's still quite significant. But
yeah, exactly, yes. Because the wavelengths, in generally speaking, the wavelengths, because they didn't start from zero, the initial wavelength. So the confidence is a little bit almost lower than the ripple wave height, because they often start from zero.
Yeah, okay, that makes sense. So I'll pop back over to the chat where we have our next question coming from Mariano Ramirez at George Mason University in Virginia. And he says, that's fascinating. Did you record remotion and remobilization of the initial clay besides the accumulation below the wave ripples?
Sorry, can you say again the question again, please?
Absolutely, yes. Did you record remotion and remobilization of the initial clay?
I can't understand. What do you mean immobilization of the initial clay? Sorry.
Yeah, I guess he's just wondering if the remobilization, so the reworking, let's say, of the initial clay, if you took a look at what was happening to that clay besides just the accumulation below the wave ripples.
Yeah, the side, yeah. Sorry, I still can't understand these questions.
Mariana, if you want to send your question to everybody.
Yes, please.
I realized
yes, please.
I got it as direct message. And then you can just elaborate a little bit. So yes, I think Val has one more question, if he may, and he may. So we'll go to that one first.
Yeah.
On the slide with Jacko's current ripples, high clay content ripples are much more straight crested than your combined flow ripples with high clay content, which were more discontinuous and nearly barconoid shaped. Why is that so?
Yes, let's come back to these photos. I think because the ripples dynamics under the current and the combined flows are different. In our experiment, we use the wave dominant combined flow. So in Bass 2013 current ripples, they look like the incipient stage as the pure sand current ripples, because in the incipient stage, the current ripples are two-dimensional. So that's why they looks like different from ours. And in ours, the ripples looks like a barking shaped, which like a little bit like not like the 3D, not like a two-dimensional. That's what I think is because they still don't emerge together to form this two-dimensional. If I come back to my slides to this one, if you can see, this is a clay content lower than 12.3. So these ripples are started to emerge together and form the two-dimensional ripples. So that's what I think the difference.
So you think that the ripples from Jacko's work are more of an incipient stage?
Yes, exactly. This what we guess. This ripples is in the incipient stage, because if we compare to the Jacko's earlier work for the clean sand ripples, Jaco said, and research shows the incipient ripples are 2-dimensional and then gradually transform to 3-dimensionals.
Okay. And Mariana, we see your comment, but Juju just needed a little bit more information on what you mean by remobilization. So if you want to add a comment to that.
Yeah.
So I have one of my favorite comments, which I'll ask you as well.
Yes.
So what do you think, or what do you expect the results would show if we started to add other things into the system, like organic material?
Oh yes, if we add some biological cohesion, especially for the EPS, as we know, the EPS has quite strong cohesion compared to the clay we used in our experiment was kaolin clay with very weak cohesive. So as you answered, if we add some, even just a little bit amount of the EPS in the bed, I think they will increase the threshold value. So I think, it decreased the threshold and content. And for example, if we just add 0.1 EPS, the threshold bed cohesion may be decreased. And so I guess just at the 6% under the similar hydrodynamic condition, I think if we add the EPS in the bed, this kind of ripples could be generated even at the very lower clay content. So that you can observe the discontinuity in a very lower clay content.
So you're thinking that threshold value might be halved?
Yeah,
I think that's
what I guess. Yeah, we should do some more research about that. This is just what I guess based on the experiment.
Yeah, I know you have a little bit of work also in the sort of biotic zone as well. So combining those two might be a really fascinating way.
Actually, the biological parameters is very important if we want to extend our laboratory studies to the field work.
Absolutely. Okay, we got another question from Catherine Giles. Thank you, Juju, for an interesting talk. How does your system compare or contrast to one that produces heterolithic bedding?
I think this way, because in our experiment, we used the consistent hydrodynamics from round 1 as a control experiment. So for round 1, and as you can see in the pure sand clean, in the clean sand bed, we didn't find any significant delay in the ripples formation. And so I think just in the experiment, the delay in the ripples formation just because of the cohesion and better cohesion in the bed. Hope this answer your question.
Okay, so if there's any more questions, please feel free, anybody out there, to type them into the chat, and we will get to them before signing off. In the meantime, I want to thank you all for joining us for this week's SEDS Online webinar. Juju, thank you very much for this wonderful presentation. We really appreciate you coming on and giving us your take on these flume experiments. And everybody, don't forget to join us next Wednesday when Sitzka Battenberg will be discussing orbital forcing in greenhouse climates. And thank you. We're getting a lot of thank yous in the chat. Jaco also gives you, I think he gave you some clapping emojis earlier as well. So
thank you, Jaco.
I think everybody really enjoyed it. Thanks again, and we will see everybody in the audience next week.